Good morning. Today we are going to see the possible theory questions. I may not claim that questions will be from this video only, but most of the questions I am going to try on unit number 1 and unit number 2, which may be asked in your in-sem examination. So we will go one by one questions. So we have explained torsion reinforcement in three conditions. So if you will go to Annex D, and in that Annex D, they have mentioned torsion reinforcement. So torsion reinforcement is required for restrained slabs. It is not provided to simply supported slabs. And they have mentioned D-1.8, D-1.9 and D-1.10 as the clauses for torsion reinforcement. So we will see in detail. So torsion reinforcement is required in the restrained slabs. The corners are categorized in three categories as per IS 456 Annex D. In Annex D, clause number D-1.8, D-1.9 and D-1.10 give the details of torsion reinforcement. Now I have shown, I will consider this slab as S1 and I have different types of corners in this. So I have this corner with both ends discontinuous, or we have this corner where one edge continuous, other edge discontinuous, and this we have both edges continuous. So now I will mention corner A where my both edges are continuous, and when both edges are continuous, therefore no torsion reinforcement is required. This is given in D dash 1.10. So what happened actually, whatever torsional moment developed by this slab will be balanced by this slab. Similarly, that is for this portion, this edge. Similarly, for this edge, balanced by this edge, and no, we can say that is resultant torsional moment available over here, and therefore we are going to get no torsional moment, and therefore need not require to provide any torsional reinforcement. Now, if we will go to torsion corner B, now, if we will go to clause number D-1.8, where we have both edges discontinuous, they have explained how you have to provide this torsional reinforcement. First, you have to provide torsional reinforcement at top also and bottom also, which is in square mesh. So this is most important one. And size of that square is 1/5 of the shorter span. Means we are going to say that is LX. So Lx by 5, this will be size of the mesh. Consists of two layers parallel to the sides of a slab. Means we have these two sides. So I have to provide, if I will draw, so I have to provide this of Lx by 5 and then should be in two layers. So you can see this. So I have this as one layer which is parallel to this side, and then I have second layer which is parallel to this side. So this is one mesh. This should be provided at top also and at bottom also. Means total we have to go for four layers. Two layers at top in top mesh and two layers at bottom in bottom mesh. What will be requirement of steel? So it should be 3/4 of ASTX. So they have mentioned there AST maximum in at mid span. So AST maximum at mid span, that is ASTX only, and therefore I have directly written over here that is ASTX. Then we have corner C. Now this will be one edge continuous, other discontinuous, which is given in clause number D-1.8. So now torsional reinforcement is required, half the reinforcement required for corner B. That means Half means whatever spacing you have. Here also you have four layers. That means two meshes. Again, two layers in each mesh. Only spacing becomes half. Spacing in C equal to half of spacing in B. Remaining things are same. So these are the torsional reinforcement which we have to provide in a restraint slabs. Then we have question, discuss the conditions for design of one-way slab using IS coefficient. Now if we will go to clause number 22.5, they have mentioned these conditions. And if these conditions are satisfied, then we have to use table 12, which gives coefficients for bending moment, and table 13 gives coefficients for shear. Now, what are the conditions? In following situation, IS code coefficients are used. First, exact analysis is not required. Now you can see here, these are mentioned, things are mentioned over here. Unless more exact estimates are made. Means if we are not going for exact analysis, we can use this method. First. Second, minimum three spans are required. You can see which support substantially uniformly distributed load. So I can mention it again. Minimum three spans. And here they have mentioned over three or more spans. They do not differ by more than 15%. So we can have this span should not be differ more than 15% of the longest. They have mentioned over here. Or you so we have this as third. Then we have fourth. They have mentioned over here, that is redistribution referred to 22.7 shall not be permitted. And then we can mention fifth also, only applicable for UDL. Only applicable for uniformly distributed load. Uniformly distributed load. If you have any point load in between, then you cannot apply this method because they have mentioned here substantially uniformly distributed loads. So we have these are the five conditions. When we can are satisfied, then we can go with one-way slab with IS code coefficients. Then discuss the conditions for flange sections, or everything is given actually in IS code. You have to learn IS code properly. So we have 23.1 T and L beam. Now when we have T beam, when you have slab on both sides. Slab on both sides. And then when L beam, when you have slab on one side. And if I will say flanged, then it applicable to T also and L also. So now we will go one by one. In following situations, beam is considered as flange beam. The slab and web of the beam shall be casted monolithically. They have mentioned over here. The slab shall be cast integrally with the web, or the web and the slab shall be effectively bonded together in any other manner. So this is first. What is second? Now you can read it. If the main reinforcement of the slab is parallel to the beam, transverse reinforcement means if main reinforcement of slab is parallel to this, here you can see if the main reinforcement of the slab is parallel to the beam, we have to provide, means if it is perpendicular to the beam, main reinforcement of slab is perpendicular to the span of the beam, then it acts as flange beam. We need not require to worry about it. If my main reinforcement of slab is perpendicular to the span of the beam, then if I will draw this, so we have this will be my one-way slab. And if I will say we have this will be continued. Now you can see Yeah, I will again continuous here. Now my main reinforcement as it is one-way slab will be in this fashion. Now this is perpendicular to this beam. So this will act as T beam because we have slab on both sides. And my reinforcement, main reinforcement is perpendicular. Now if the main reinforcement of this slab parallel, so this I have mentioned wrongly. If it is parallel, then to the span of the beam, so just I will rub this portion. If it is parallel, then that is mentioned over there. That is the distribution reinforcement is provided 60% of the main reinforcement that is mentioned. Such reinforcement shall not be less than. So when it is parallel to the span means main reinforcement of this slab. Now this slab, now you can see we have parallel to this. So in that case, my distribution reinforcement, so I have this as distribution reinforcement, this should be 60% of main because this is Lx one way slab, this is Ly, so my main reinforcement is parallel to Lx and therefore this beam is T beam and then this we have to provide 60% of main reinforcement and then it will act as flange beam. Then we have next question. What are the assumptions? So we have this will be what are the assumptions? Assumptions in limit state method. Now actually these are given on IS 456 in IS 456 page 69. So first we have plane section normal to the axis remains plane of bending. So now you do not go in detail with this. So if we have this beam and when this beam load is applied to this beam, then this beam will bend like this. And then your cross section will not be rectangle because if I will take cross section, then we do not have cross section because it is bent. So my cross section is not rectangular, but we are assuming it. Then the maximum strain in concrete at the outermost compression fiber is 0.0035 in bending. These are given in IS 456. Try to write in your words. An acceptable stress strain curve is given in figure. Now you can see this figure. So we have figure 21. So I can mention here figure 21. And for design purpose, the compressive strength of concrete in the structure shall be assumed point. This is most important. 0.67 times the characteristic strength. The partial safety factor gamma equal to 1.5 shall be applied in addition to this. And so we have to use this curve. So just mention we have to use this curve. So you can write here, this curve is used. Then we have next, the tensile strength of concrete is ignored and the stresses in reinforcement. So this value representative stress strain curve. So that I have not shown here. So if we will go to figure 23 and 24, then that is given for, sorry, 23A and B. So this is for mild steel. And if we will go for torch steel, then we are in this fashion. Likewise. So this is for HYSD bars. And we have this as for mild steel bars. And we have partial safety factor as 1.15. Then maximum strain in the tension reinforcement Fy upon 1.15 into ES. So these are the assumptions which are related with your limit state method. Derive stress block parameters. So actually this already we have seen. If we will go to the unit test question paper and in that we have explained this, we have divided it into two parts. One part we have that is rectangle and another part we have that is parabola. So 0.45 FCK into 3 by 7 and this is 2 by 3.45 FCK into 4 by 7 and this will give value. Now we are going to consider their CG from top. So for this rectangular section, we have from top that is half of this one. For rectangle, it will be half of 3/7 XU. So half of 3/7 of XU. And for parabola, we have values that is 3/8 of 4/7 XU plus 3/7 of XU. Means from here actually we have this value 3/8 of 4/7 XU. And we have to take from top. So we have to add in this 3/7 of XU. And from this we will get X bar as 0.42 XU. Then derive the expression for neutral axis factor, lever arm factor, and moment of resistance factor. So we have to draw this diagram. Then we have this as strain diagram. Then from the geometry, so we are going to consider similar triangles. So by considering similar triangles, we have this as XU max upon D minus XU max. We are considering these two triangles. This is first triangle, and then we have this will be my second triangle. So first triangle we have XU max, corresponding to this we have 0.0035. Second triangle we have D minus XU max, corresponding to this we have 0.002 plus Fy upon 1.15 ES. Then we have that is dividendo. So dividendo means we are going to add numerator in denominator, and from this we are going to get this XU max, that is equal to 0.0035 upon 0.005 plus 0.87 Fy upon 2 into 10 raised to 5. And then we have just modified it where Ku max we have this value, that is 0.0035 upon 0.0055 plus 0.87 Fy upon ES. So it only depends on grade of steel and not grade of concrete. Then we can have lever arm factor. So as we know, if you remember your diagram of compressive force and tensile force, we are in this mesh. So we have somewhere here map C, and here we have T. And then we have this distance that is equal to D. Now we have calculated this value from top and we got it as 0.42 XU. And what is lever arm? So lever arm, that is the distance between the two parallel forces which are equal in magnitude and forms a couple which is known as moment of resistance. And this we have D minus 0.42 XU max. So for balance section we are mentioning over here. And then we are going to substitute XU max as D, Ku max into D. So here we have mentioned Ku max into D, and from this we will get D common, and then we have lever arm factor as this portion 1 minus 0.42 Ku max. So that is Ju max. And then we have third, that is moment of resistance factor. So we have moment of resistance 0.36 FCK XUB. So this will be my compressive force. So Cu, and this is my lever arm. And then if we will put the values, we have XU as XU max, Ku max into B, D minus D 0.42 XU max. Then we have taken D common, D we can have, XU max. This is correct. So I have this as XU max only. So this is XU max, and now I will put this XU max, that is equal to Ku max into D. Here we will take D common, and from this we will get 0.36 FCK Ku max. This BD and D common from this taken outside, and then we have this portion that will be your moment of resistance factor. So Ru max, and we have Ru max this value. So if you asked your neutral axis factor, then you can find these values directly, that is 0.0035 upon 0.00 any grade you may have given. So you have to find using this formula. So sometimes such question may be asked. Then Ku max we have 1 minus 0.42 Ku max or Ku. If you are given a value of Fy, then we can get this value, and Ru max you have to find using this formula. Then we have last question I am taking in this video, that is differentiate between working stress and limit state method. So description, working stress method and limit state method. So basis of design. So in working stress we are using elastic theory for the design, and here we have probability theory and statistics. Then we have stress levels. So as we know here, we are using stresses are within elastic limits. Working stresses we are going to consider. Means if we will draw a diagram, so already I explain it. So if I will draw a stress diagram, then we are going to consider till elastic portion. So whatever plastic region we have, that plastic region we are going to neglect in working stress method. And in limit state, we are going to consider your plastic region also. So design is based on ultimate maximum strength capacity of the materials. Then we have factor of safety in working stress. We have used single factor of safety uh, in this, that is for materials only. We are not used factor of safety for loads, whereas on material strength I mentioned. And then in limit state method we are using part safety factors for loads and materials, and therefore we are mentioning it as partial safety factors because it is applied partially to both material, for both materials and loads. Then economy, as we are using only elastic region of the strength of the material, and therefore your sections are large compared with your limit state method, and therefore as sections are large, as considering only elastic region, so these are not economical sections. Whereas if we will go to this, then we are more economical because we are going for realistic consideration of loads and material strength, and therefore my cross sections are smaller in size compared with your working stress method, so it is more economical. Then we have serviceability. So serviceability criteria is actually not considered, but here mentioned is inherently ensured. Why? Because here cross sections are large, and we have delta is equal to, if I will consider concentrated load, it is WL cube upon 48 EI. And if I will consider that is UDL, then I have this value 5WL4 upon 384 EI. And in both you can see in this we have I moment of inertia, that is in denominator, and as in this we are considering only elastic region, and due to this our cross sections are large, and due to these large cross sections my moment of inertia is large, and automatically my this serviceability criteria is satisfied, so therefore it is mentioned inherently insured. Whereas here explicit check for serviceability we are considering, that is for deflection cracking, that is required. And then we have last material utilization. Here we are using less efficient or strength, we are not using full strength of the materials, whereas here we are using more efficient, better utilization of material compared with your working stress method. So these are the some questions which I feel may asked in the examination. Therefore, I have prepared this video. All the best for your in-sem examination. Thank you.